Hi guys, welcome back. Let's jump in. This is a little bit more complex than the last couple of examples that we've used doing integration using partial fractions. But really, it's not too much trickier than the previous problems we've solved. The only thing that we need to make sure that we do is to actually to factorize this denominator here so that we can find each of those partial fractions. All right, so to factorize this, what are the factors of -6 that are going to add to get -5? That's going to be x minus 6 and then x plus 1. And so if I was to expand that out, I should get x squared minus 5x minus 6. So let's pop this now into our denominator here. So x take away 6 and then x plus 1. Dx. And then let's go ahead and rewrite this using our partial fractions. So if we were to try to find this value here, this is going to be equal to some number over x take 6 plus some other number over x plus 1. And we're going to cross multiply now so that we get a x plus 1 over x plus 1 x minus 6. Plus some number times by this other denominator, because we're going to cross multiply, over x plus 1 and then x minus 6. So now we're going to multiply everything through by that denominator. So we're going to get 6x take 1 is equal to a x plus 1 plus b x plus 6. So now we're going to go ahead and we're going to substitute in values of x that are going to eliminate a and b. So let's eliminate b first to solve for a. So if we substitute in, that should be x minus 6. Let me just fix that real quick. So we're going to substitute in x is equal to 6 first, and then for our other value, we're going to substitute in x is equal to -1. So let's go ahead and I'm going to do this substitution now. So a is equal to 5 and b is equal to -1. So if we just scroll up now, what we can do is we can substitute 5 into this value here and -1 into this value here. So let's rewrite that. So let's go ahead and finish this off now. So the integral of 5 over x take 6 dx is going to be 5 ln, I always do that, it needs to be the absolute brackets. We can't have a negative value for a log. So this is going to be minus ln x plus 1 plus c. And there we go. So that is going to be our solution. So let's jump in and let's keep doing some more of these trickier examples. But this time I want to try using some repeated linear fractions. So if we had like perfect squares, for example, that we were dealing with. Okay, I've got an example here, and the reason that we can't just use the previous tricks that we've done is because if I wrote this out as, so it's just going to be 4x plus 5 over x plus 2 times by x plus 2, if I was to rewrite that using that notation, well, we can already just add the numbers together since the denominators are the same. So we have to kind of come up with a way around this, and we've done that by making sure that that second factor, that repeated linear factor, is actually ax plus b squared. And that's actually going to allow us to find some values here. So let's go ahead then and let's write this as a over x plus 2 plus b over x plus 2 squared. So that's my tip for these repeated linear factors. If it was ax plus b to the power of 3, then you could do ax plus b and then ax plus b squared and then ax plus b cubed. So just again, using those partial fractions with those repeated linear factors to solve for a, b, and c. All right, let's go ahead though and let's do this example first. So now I need to cross multiply. So to do that, we are going to multiply this one here by x plus 2. And this is now going to become x plus 2 squared plus b over x plus 2 squared. So we can rewrite this now. If we multiply out by x plus 2 squared, that will remove all of our denominators, and we're going to get 4x plus 5 is equal to a x plus 2 plus b and we're just going to leave it as that. All right, now this one's a little bit trickier. So what we could have done is we could have multiplied this actually by x plus 2 squared and then multiplied this side by x plus 2. But I want to see if I can solve this using, you know, this pretty simple form here. And so what I'm going to do is I'm going to let x equal to -2, and I'm going to substitute in, and that's going to help me to solve for b. So now what we can do, because we obviously can't substitute in any value of x to eliminate this b term, we already know what this value of b is to work out a. So what I'm going to do is I'm actually going to expand this a out across the brackets so that I get 4x plus 5 is equal to ax plus 2a minus 3. And this here is going to be our constant term, where that's going to be equivalent to our 5, and then this here is going to be our coefficient. So if I write that 4x is equal to ax, then hopefully I get a is equal to 4. So let's just double check that. If I have 5 is equal to 2a take 3, then I'm going to get 8 is equal to 2a, and then I'm going to get a is equal to 4. Good. So the terms do match. So that means that a is going to be equal to 4. So let's substitute these back into this expression here, and then let's go ahead and find the integral. Okie doke, so just substituted that in. Let's go ahead and find the integral. So the first one is going to be 4 ln x plus 2 minus, now this one here, we've got x plus 2 to the power of -2. So we could use our chain rule here, and hopefully you'll be able to appreciate that I'm just going to add 1 to this power and then divide by the inside function, by the derivative of the inside function. So that's going to give me -3 lots of x plus 2 to the power of -1 divided by -1, and then I now have my function. So let's rewrite that. And there we go. So I now have my completed integral of the function 4x plus 5 over x plus 2 squared. Let's do another example using these repeated linear functions, or repeated linear partial fractions. Okay, and what we need to do for this one, as you can see, is we need to factorize this bottom denominator here. But this is actually a perfect square, and so I know this is going to be x plus 3 squared. So let's rewrite that. Okay, so 2x plus 1 over x plus 3 squared is going to turn into the partial fractions a over x plus 3 plus b over x plus 3 squared. So again, I'm just going to cross multiply one of these. So I get a x plus 3 over x plus 3 squared plus b over x plus 3 squared. And that's going to be equal to 2x plus 1 over x plus 3 squared. And so now what we can do is we can multiply the entire equation by the denominator, and that is going to just let 2x plus 1 equal a x plus 3 plus b. Let's not substitute in x is equal to -3 this time. Let's just straight up go ahead and expand that factor out so that we have 2x plus 1 is equal to ax plus 3a plus b. And again, this value here is going to be a constant, so it's going to equate to the constant term, and then my variable ax is going to equate to my variable 2x. So a is equal to 2. Now that I know that, I can substitute that into my value for a here, so that I have 1 is equal to 3 lots of 2 plus b. Subtract 6 from both sides, I'm going to get b is equal to -5. And so now we can substitute each of these back into our original equations, and we can go ahead and find the integrals. It's feeling a little bit lazy, didn't feel like rewriting it, so we're just working straight from here. So this is going to become 2 ln of x plus 3, and then this is going, oops, that should be a negative. This is going to become -5 over, oh no it's not, because when we integrate that's going to become like that. There we go, plus c. All right, I'm just going to quickly double check that. So I've checked that using the online calculator, and that is the correct solution. So apologies for bungling my way through that one a little bit there. But just if you are curious about the calculator they use, literally it's just called like integral-calculator.net or something like that. It's like if you just Google integral calculator, it's the first result that pops up. There's been a few issues with some of the solutions in the textbook, so that's why I've been using that, just to make sure that I do have those correct integrations. They also have one for derivatives if you were curious about that as well. And they have fully worked solutions using integration by parts or integration by substitution, depending on what the best method is. So please use that as a study resource. I think you'll find it really, really helpful. Okay, so I'm going to jump into the next video now. I'm going to do a pretty tricky one. I don't want to call it complex unfamiliar for reasons I've sort of talked about previously, but it will be a high-level question. So keep an eye out for that video. All right, guys, I will see you in the next one. Have a great day.